Okay, so for spherical electric fields, let's say, we had a spherical object, we want to find out, what the electric field is. We can calculate that using kq over r squared to get what the field is. And so q represents the charge that's producing the field, r is the radius away, and k is the constant that we use based on the permittivity of a vacuum. And so, and then we'll get a certain amount of electric field from that. So this is a little bit different than what we just did. If this is, let's say we have a Van de Graaff generator, and here's it's positively charged. If we're a certain radius away, let's say we're right here, what is the electric field of that spot? Well, we know that it's going to be pointing this way, right, at a certain amount of newtons per coulomb. And this will help us calculate that, what that is. Whatever the Q is of this, however far the radius is from here, we can figure out what the electric field is at that spot at that particular angle. So what is the strength and direction of electric field? That is 1.4 times 10 to the negative 8 meters to the right of a positive 45 microcoulomb charge. So let's go ahead and draw the charge. And then we want to find out what is the field at this spot. So there's actually nothing there, right? There's nothing there, but we want to find out what is the field at that spot. So the first thing that we can say is, okay, if I placed a positive test charge here, where will it go? Well, it would go to the right. So whatever answer that we're going to get, it's going to be blank newtons per coulomb to the right. That's going to be the field. We just need to know the numerical value. And so kq over r squared, we know it's 45 microcoulombs. And we know that the radius is 1.4 times 10 to the negative 8 squared. And we can calculate the two, and then we'll get 2.1 times 10 to the 21st newtons per coulomb. And then the direction would be to the right. So the same principle of superposition works with electric fields as well. Let's say we have more than one charge and we have fields being generated there. It's going to be the vector sum of those two fields to produce the resultant field. And again, we'll do vector addition. These are vectors, right? So we're going to need to get the x and y components as needed. So, and again, the field lines are not curvy. Well, they are curvy, but the vectors themselves are not curvy, right? They're the tangent lines at whatever given point there are. And we can get, the resultant fields. All right, so let's say that we have a negative 5 microcoulomb charge at negative 2. We have a positive charge at positive 2, and we want to find what is the field here at the origin. What is that here? So just like we did before, we pretend like one's not there, and we calculate the field, and then we pretend the other one's not there, calculate the field, and we can figure it out. So yeah, so for this one, if we want to find the field due to this charge, right, we place a proton here. We say, okay, where would it go? Well, the proton would go to the left. So it would be blank newtons per coulomb to the left, which we calculated here. 5 microcoulombs, and then 0.02 meters from the centimeters, and then we square that. And then what we say is, okay, now we're going to pretend this one's not here, and this is the only one here. If we place a proton here, where would it go? Well, the proton would also go this way. So when we calculate this one, it's going to be blank newtons per coulomb to the left. And that's what we get there, 1.125 times 10 to the 8th newtons per coulomb to the left. So they're both to the left, so the superposition would be adding up those two. And the field at the middle is going to be a resultant of those two. Both are to the left, so both fields add up together for a total resultant there. All right, so for this one, let's say we had a triangle, and well, let's say we had two charges and we want to find out what is the field at the top of this triangle. So what we would do is we would say, okay, if I have a test charge here, let's pretend this one's not here. Where would this go? Well, the field would be up at an angle like this, right? And we'd have a certain amount of x component, certain amount of y component. And then we'd say, okay, let's pretend this one's not here. Then we would say, okay, place a test charge here. Where would it go? It would go off like this, right? you know, and you get the x value, the y value there. And so what you would want to do is, you know, get the total x, total y, and then bring them together. So yeah, go ahead and pause the clip. Give this a try. You got all the information that you need there. Just be careful with your units and give this a try. And then when you're ready to check, you can hit play to continue. All right, so we have our forces, and this top, well, the fields rather. You know, if we had a proton here and see where it goes, we would go up like this, right? So we would have our x value, we would have our y value. The total amount is this, and then our x component of that field would be 7.5 times 10 to the 7th newtons per coulomb, and then the y component of the field would be positive 1.299 times 10 to the 8th newtons per coulomb. Now, if you look at the other side, right, if we ignore this one and we just, you know, we place a test charge right here, it's going to go off like this, right? And so the field, we can break it into the x and y, and we get this much to the left and this much to the north. So if you notice, the x fields actually cancel each other out. This one's to the right, this one's to the left. So if we added those up together for the total x, total y, the total x would come out to be 0 because this and this field would cancel each other out. For the y, we would add up our y values together, and we would get a total field of 2.6 times 10 to the 8th newtons per coulomb to the north. Okay, so let's take a look at this one here. We have a 350 microgram bead that has an excess of 300 electrons, and we want to find out, you know, what the acceleration would be on that particle. So we're going to use that same information that we had, and this is for an object that's placed in there that's, you know, a 300 excess electron bead. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so force equals EQ. We know that the charge there is 300 times the elementary charge, and the elementary charge is 1.6 times 10 to the negative 19th coulombs. So we have our charge, we know the field strength, and we know the total charge, and so this is going to be the force on it, because the field is going upwards, but it's a negative charge, and so the force will be downwards for a negative charge. Because remember, with the field, we define a field based on placing a positive test charge, a proton there, and seeing where it goes. And then we want to find the acceleration, right? So we know the mass of the bead, and we know the force, and so we can figure out the acceleration of the bead, and our acceleration is 0.0356 meters per second squared downwards.